Good morning guys, and welcome to today's worked exam answer video. As these seem to be my most popular videos and I get requests rather frequently for time of flight mass spectrometry calculations, I thought it would be good to follow up the one that I did fairly recently with another example here for those people who are trying to improve their time of flight calculation responses and how to work through those. So we've got another more complicated one here, just like the one that I covered in my latest video on these, whereby we have got different isotopes of the same element, and using information about one of the isotopes, we're going to need to get the kinetic energy of both of the ions, and then using that kinetic energy we can then get the time taken by the second ion to travel down the same flight tube. So as I did in the last video, we've got colour for one of the isotopes, colour for the other isotope, and then a colour for information that pertains to both of them. So that's where I'm going to start today's video. So we're told that a sample of antimony, which might be an element that you're not very familiar with, has a strange symbol of SB. Anyway, a sample of antimony is analysed in a time of flight mass spectrometer and is found to contain two isotopes. One of them has a mass number of 121, and I'm going to colour that in orange, and the other has a mass number of 123, and that one's going to be purple. It says after electron impact ionization, so at the start of the process, these have become ions by having one of their electrons knocked off. All of the ions are accelerated to the same kinetic energy, and that is key in terms of how the process works, but it's also key for us to know how to approach this calculation. The kinetic energy is going to be the same for both ions, so if we can work out the kinetic energy from the information given about the 121 isotope, we've then got that kinetic energy which we can then use for the 123 isotope. So all of the ions are accelerated to the same kinetic energy, and then they travel through the same flight tube that is 1.05 meters long, and that applies for both of them. And then we're given the time of flight for the 121 ion and told that that takes 5.93 times 10 to the minus 4 seconds to travel through that flight tube. Then we're given the kinetic energy equation, as we tend to always be, where kinetic energy is a half times the mass times the velocity squared. We are reminded here that mass needs to be in kilograms, and speed or velocity will be in meters per second. Now the length of the flight tube has been given in meters and the time has been given in seconds, so that's all good. Mass will need to be in kilograms. So the first thing we're then asked to do is calculate the mass in kilograms of one antimony 121 positive ion. That will then enable us to work out the kinetic energy. Not that it tells you to do that, but that's what you will need to recognise you need to do. And then we're asked to calculate the time taken for the 123 antimony ion to travel through the same flight tube. And then, as is always the case for these questions, because we need Avogadro's constant, it is going to be given to us. So we know that we've got to start with a mass of one of those 121 ions, and we know what the end goal is. As I said, the key thing that you need to recognise is that the way we're going to work this question is getting the kinetic energy for both of the ions. Then we'll have all the information that we need. So, starting with the mass of the 121 antimony ion, anytime we're working out the mass in these questions, mass, as we know, is equal to moles times the MR. Now we don't have the moles, but there is another way that we can work out moles, which we're going to substitute into this equation, and that is to use the equation that moles is equal to the number of particles divided by Avogadro's constant. So that's what I'm going to sub in there instead of my moles. And then we're not going to use the MR because we're not dealing with a compound, we're dealing with an element that has isotopes, so we're going to use the mass number. That will give me the mass in grams. And as it's hinted at in 3 separate places, we need to get the mass into kilograms. So once I've got my mass in grams, I'm then going to divide it by 1,000. So it says calculate the mass of 1 ion. So we'll always be using 1 for our number of particles here. Avogadro's number, always given to us, but I'm sure that you will be becoming familiar with it now. Apologies, my English is failing me as per usual. And then the mass number for the 121 ion is 121. And as I said, that will give me my mass in grams, which comes out as 2.009. So I'm going to go for 2.01 for 3 significant figures, times 10 to the minus 22 grams. And then to get it into kilograms, we're going to need to divide that by 1,000. So it's going to become 2.01 times 10 to the power of minus 25 kilograms. And I'll pop a little note on there. But to get to there, we've divided by 1,000. Okay. Now that we've got the mass of one of those 121 antimony positive ions, we can then use this equation here, where kinetic energy is equal to half mass times velocity squared, to get the kinetic energy, because we've now got the mass of the 121 ion, we know the length of the flight tube, and we've got the time it takes for the 121 ion to travel down that flight tube. So the equation that they haven't given us here, obviously, they tend to only give you the kinetic energy equation out of the 3. The other one we're going to need is that speed or velocity is equal to distance over time. Now that's an equation you're probably very familiar with from GCSE physics. So that's possibly why they don't give you it, but that's one we're going to need as well. Now, some people will be very happy substituting that into there and making it a half mass bracket d over t bracket squared. Some people will want to work out the velocity first and then sub it into here. There's no right or wrong, it's whatever works for you. I'll write it out with it subbed in, but please feel free to obviously work out the velocity first and then sub that number in. So we've got kinetic energy equals a half mass times the distance over time squared. So that is going to be a half times 2.01 times 10 to the power of minus 25 to the mass of the 121 ion, and then we're going to be timesing that by the distance, which is 1.05 meters, and the time it takes for the 121 ion to travel through the flight tube, which is 5.93 times 10 to the minus 4. And then all of that in that bracket, which will give us the velocity, then needs to be squared. And I'm partly doing this to save space on my piece of paper, but we could have very easily worked out what 1.05 divided by 5.93 times 10 to the minus 4 was first, and then that would give us the velocity. Then we can put that number into here, and then that would be squared. As I said, no right or wrong. That gave me a kinetic energy of 3.1498, so we're going to go for 3.15 times 10 to the minus 19 from my 3 significant figures, and that will be in joules. Now, that is the kinetic energy for both ions, and we're reminded of that in the question. All of the ions are accelerated to the same kinetic energy, but it's also an expectation that you'll understand kind of that is how the time of flight mass spectrometer works. We generate the ions, we accelerate them using a negatively charged plate to the start of the flight tube so that they all have the same kinetic energy, because by them all having the same kinetic energy, it means that they will be separated within the flight tube. Because some of them will have higher masses, they will therefore move more slowly, their velocity will decrease, therefore they won't get to the end of the flight tube and hit the detector as quickly, whereas the lighter ions, they will be able to travel faster, so their velocity will increase. And so the mass and velocity have an inverse relationship, so higher mass, decreased velocity, lower mass, increased velocity, to keep the kinetic energy the same. And that means that the ions will hit the detector from the lightest mass first to the heaviest mass last. So having the same kinetic energy is really important. Now we can apply that kinetic energy along with the length of the flight tube and the mass of the 1, 2, 3 ion, which I'm going to have to work out now, to get the time taken for the heavier ion to move through the flight tube. So I'm not going to rewrite out all of my equation, but what I am going to do for clarity is just go back and say that this was the mass for the 121 antimony ion, whereas now we've got to work out the mass of the 123 antimony ion, and again that's going to need to be in kilograms. So first of all, the mass in grams is going to be equal to 1. It's always 1 particle for these calculations, divided by Avogadro's constant, and that would be my equivalent of my moles, and then times that by the mass number, which now is 123. That gives me an answer of 2.04 times 10 to the minus 22 grams, which is then 2.04 times 10 to the minus 25 kilograms. And again, all I've done to go from grams to kilograms there is to divide by 1,000. Now we should expect the isotope with the higher mass number to be heavier, and it is, so that's always a good sign. Our heavier isotope is heavier in terms of grams and kilograms, so that's a good sign. And now we can use the kinetic energy equation again, but rearrange it to get velocity. So the velocity of the 123 ion is going to be equal to 2 lots of the kinetic energy if we move the half over first. Then we've got to divide that by the mass that we've just worked out for the 123 ion. That will then give us the velocity squared. So then once we've worked all of that out, we're going to need to square root our answer. So we're going to have 2 times the 3.15 times 10 to the minus 19 that we worked out for the kinetic energy a little bit earlier. We're going to divide that by the mass that we just worked out of 2.04 times 10 to the minus 25. And then I'm going to need a series of brackets here. We're going to square root that. And again, you can do this in stages on your calculator. Don't have to do it all in one go. Sometimes doing it all in one go is worse. So I did this bit first inside the bracket, got an answer, then I square rooted it, just to make sure that I'm not missing out any essential brackets, and that gave me a velocity of 1,756.2, and the velocity or the speed will be in meters per second. And we're very nearly there now, because now we've got the velocity, we've also got the distance, so we can rearrange this equation to give us the time. So time is going to be equal to distance divided by velocity. The distance, same length of flight tube, is 1.05. The velocity is what we've just calculated, 1756.2. And then that gave me a time of 5.9788. How many significant figures am I going for? Got 3 for the distance. We've got 3 significant figures for the time of the lighter isotope. Yes, Avogadro's constant is given to 4, but the time and the distance are given to 3. So I'm going to stick with 3 significant figures. So 5.98 times 10 to the minus 4 seconds. Which again, let's just see, does that make sense? The time for the 121 ion was 5.93 times 10 to the minus 4. The heavier 123 ion took 5.98 times 10 to the minus 4 seconds. Heavier, so takes longer to move through the flight tube. Seems legitimate to me, makes sense. So that will be my final answer. Now, in terms of considering the significant figures, nowhere in this question does it say to consider significant figures, but they will always be looking for you to do that in every single calculation that you do. So please make sure that you look back at the values you've been given in the question, find how many significant figures they all are. So 3 for the distance, 3 for the time, 4 for Avogadro's constant. We always need to use the lowest precision. So 3 significant figures here. So both of my answers given to 3 significant figures. As always, guys, any questions about this, please feel free to leave me a comment or send me an email. If you've got other examples that you want me to work through, again, please send them over to me and I'm more than happy to do that. Thank you so much for watching, guys. Hope you have a lovely weekend ahead.